lectures. So the first one on quantum silicon photonics. So this is going to be a quite general introduction about the topic. And then the second one is about how can we produce quantum state of light. Because this is one of the key ingredients, as you will see in a while. So the topic is quantum silicon photonics. I should thank the people in my group who are working on this topic with me and who essentially have prepared all my slides. So specifically Alessio Baldazzi and Stefano Azzini and Chiara Michelini. So what is the next step in our discussion about silicon photonics? So now what we are going to do is that we are moving from classical integrated photonics to quantum integrated photonics. And the idea of quantum integrated photonics is to develop a system that is able to manipulate single photons within a silicon chip. So therefore, what we are trying to do is that we are trying, as with standard silicon photonics, we are trying to integrate the quantum optics experimental setup like this one. So this is one of our setup into a very small integrated circuit. And as you will see in a while, so the key components that are essentially making the integrated photonic circuits are silicon waveguides. So we are essentially dealing with the same platform as with silicon photonics in general. So in classical photonics, so what we are using are the properties that are predicted by the Maxwell equation on the propagation of light, on diffraction of light, of interference of light, and the coherence of the light. But then the situation changes if now we move from classical light properties to quantum light properties. In this case, in addition to those concepts, we need also to discuss what is quantum superposition, what is quantum entanglement, and what is quantum interference. So each time we speak about quantum, so what we are considering are some strange phenomena that occurs on the nanoscale. And in order to describe those strange phenomena, what we are essentially using are the theories that have been developed by Schrödinger, by Planck, by Heisenberg, by Einstein, and so on and so forth, at the start of the 20th centuries. And so essentially, we are changing our description from wave properties of light to the quantization of the light state, meaning that now we are really dealing with single photons. So typically we say that all this quantum mechanical theory has promoted what is called the first quantum revolution. And the quantum theory has been used in order to understand the property of matter. Coming from this understanding, so few disruptive devices during the 20th centuries have been demonstrated. So in 1947, the first transistor have been developed. Then in 1959, the first integrated circuit. Then in 1962, the first laser diode. Then in 1961, the first microprocessor. And from these single components, the revolution of internet has appeared. So in 1991, the World Wide Web was implemented, and nowadays we cannot live without any connection. And so starting from this development, at the beginning of 2000, people have started to say that we are on the dawn of the second quantum revolution. And indeed, at the European level, so it started an initiative that is called the Quantum Initiative, by which people are investing strongly on quantum technology because they believe is the fact that the future is based on quantum physics. And therefore, the European Commission, almost 10 years ago, launched a program which was a flagship program about quantum technologies. And the idea here of this quantum technology program was indeed to develop a technology where people have to develop techniques and devices able to manipulate quantum effect in systems in order to impact on the technology. And so this is the heart of the quantum, of the second quantum revolution. And this idea has been shared by many other states worldwide, and should say that there is a huge global effort all over the world in order to promote and to develop quantum technologies applications. So, for example, here, so this is a cartoon made in 2022. You see that also India has a strong program in quantum technology that at this time here was worth of $1 billion. It's a very significant program. And then, so since there is such a large interest in developing this technology, also business has been developed based on quantum technology. Here is the forecast of the market increase of the quantum technology related market, and what you see here is that the forecast increase in percentage of the market is extremely significant. So 30% is even larger of the predicted increase of India in this time. And what is quite interesting here is the fact that the sector by which people are essentially investing, that is about quantum computing or quantum cryptography, so they are growing. But the actual and most important market nowadays for quantum technologies is in sensing. Okay, so quantum sensing, quantum measurements is really the market that is driven the sector nowadays. It is predicted that then, in 5 years from now, so the quantum computing and the quantum cryptography market will increase. If one should consider the size of the quantum computing market, so the prediction is that nowadays the size is quite small, but in 5 years it will grow up significantly. But quantum technology is not only quantum computing, it's not only quantum cryptography, but there are a huge diversity of applications for quantum technology. So quantum technology is really something that has the premise to impact very significant the market. So, what are quantum technologies now? Because I simply introduced quantum technologies, and now we need to discuss what are the key aspects on quantum mechanics that people are trying to use in order to enable new devices. And so here in this cartoon, I will go in detail in all of these different aspects, is briefly summarize what we want to use in order to build up new devices, meaning that in order to build up a new technology. So we want to use qubits, we want to use the properties of the quantum measurements, we want to use the properties of quantum superposition, and we want to use the properties of quantum entanglement. Okay? So therefore, the second quantum revolution is based on the intrinsic properties of a quantum system. So the first properties, that is the most important and the reason why it is called quantum, is the fact that nature is not continuum, is not a continuum of state, is not a continuum of atoms, is not a continuum of anything, but has an intrinsic granularity. That means that everything is quantized. So the energy is quantized, the light is quantized, and so the quantum of light are the photons. And therefore, so what we want to use in the second quantum revolution is the properties of the single entities that are making the nature. And since we are interested in photonics, for us, these single particles are the photons. And so what we want to use in this second quantum revolution are the properties of isolated photons. Okay? So in this laser, you have billions, hundreds of billions of photons. What we want to do is that now, no longer using billions of photons, but only one single photon. And therefore, one of the important aspects, one of the important challenge is to be able to generate those single photons, to be able to manipulate those single photons, to be able to detect those single photons. So there is a need of generate what is called non-classical light sources. Non-classical means light sources that are able to generate a single photon. Classical light sources like a laser, like a lamp, like a black body are generating a huge amount of photons. Here we want to generate a single photon. So one very easy way to generate a single photon is simply to try to manipulate the device in such a way that we are able to trigger a single electronic transition. Okay? And therefore, so what we can do is that we can take an atom or a quantum dots and then excite one electron into a high energy state and then force this electron to recombine. And during this recombination, so the electron emits a photon. And if we have an isolated atom, so we can get a source of a single photon. So this is one way to generate the single photon. Another way to generate a single photon is to exploit some spontaneous properties of the nature of the materials by which we can get spontaneously, meaning that it's not triggered by any external means, they can get spontaneously the annihilation of two photons or the annihilation of three photons in order to generate correlated photon pair sources, correlated photon pairs. So in this process, what we have that a few photons do spontaneously annihilate, and by this process, they do generate a single pair of photons. And so this is another technique that we are using. And those two techniques I will discuss in a while. But what is important is the fact that in this case, so this source is deterministic, meaning that we know when the photon is going to be generated. So whenever we have one electron in this high energy state, a photon will be generated. On the other side, this source is probabilistic, meaning that we don't know when the photon will be generated. We only know that the probability to generate this photon is given by a certain number. At the end of those two processes, what we can get a precise control of the initial state of the field. And then we make evolving the field in order to get the output states. So since we are dealing with single photons, so then by comparing classical photonics with quantum photonics, we need to be very aware of the fact that the threshold for the different phenomena are very significantly different. For example, if we consider and we compare the power of the light beam that we are typically using, in classical photonic, the power is a few milliwatts. So this laser pointer here has a power that could be a fraction of a milliwatt. Since in quantum photonics we are dealing with a single photon, the level of the power of the light beam that we are going to use is extremely, extremely lower. Okay? So we are talking about some power that is of the order of femtowatt. You know femtowatt, 10 to the minus 15 watts. Extremely small. On the other side, the properties of the light state, in the case of classical photonics, for example, if we are considering a laser beam, we have that the main property is the fact that the laser beam is coherent. So the coherence of the laser beam is the reason why we are developing silicon photonics, integrated photonics. In the quantum realm, so the most important properties of the light state is the fact that we can get a single photon, meaning that we are dealing with product states, or we can get entangled photon, meaning that we are dealing with multipartite states. And so the properties are significantly different. The intrinsic properties of the light state moving from the classical to the quantum state. Then, from the point of view of the detector, also the detectivity, the characteristic of detector should be adapted to the fact that now we are dealing with an extremely small signal power. And therefore, so that means that the detector, so the noise equivalent power of the detector, so the ability of the detector to detect a very small signal, should be order of magnitude better in quantum photonics than in classical photonics. The crosstalk, you remember yesterday we discussed about the crosstalk, and we say that we can accept a crosstalk between different channels in an optical network that is something smaller than 30 dBs. In the case of the quantum photonics, any filter that we are going to develop, the max or a filter on a signal, anything, should be able to filter out to the single photon level, meaning that now the requirement is extremely more severe. So we need to develop filters that are able to isolate the nearby channel by more than 100 dBs. And you see how those two quantities differ, which means that the requirement on the single component in quantum photonics is much more stringent than the one that we are typically used to have in standard classical silicon photonics. Then the noise level is already is as well very required. And also what you have quite importantly is that the scaling law in classical photonics are typically linear, while in quantum photonics are typically nonlinear. Okay? So that means what? It means that here, if we have 10 photons in, we can get 5 photons out. If we have 20 photons in, we can get 10 photons out. In this case, the situation is different. Here you see an N, so means that the response of the system depends on the number of photons that you have inside your system. And therefore, the output signal is not only dependent on the input signal, but is dependent also on how many photons are used in your system. And so this means that we are really going to be facing with very stringent requirements in order to implement those photonic devices. And the reason why we are asking those very stringent requirements is the fact that now we are manipulating the single photon. Okay? So this is the first properties. The second properties that we are going to use in quantum photonics is the state superposition. So state superposition is a concept that is intrinsic to quantum mechanics. Let us do an experiment. Okay, you see here we have two boxes. One box is observed. So one box is open. Is an open box, and we are observing the box from the top. Okay? The other box is observed from the bottom. And therefore, when we are looking at the box from the bottom, So what we are seeing is the bottom and then the edges of the box, while if we are looking the box from the top, what we are seeing are the edge of the box and then the bottom of the box. Okay, this is clear, no? In one case, so the box is deep. On the other case, as we go in with our finger, so we immediately touch the bottom of the box. And now I'm asking, so here, are we looking the box from the bottom or from the top in this image? So how many are saying that we are looking from the top? Okay, this side here, okay. And here, we are looking from the bottom or from the top? Huh? Bottom or top? Anyone want to decide? No, you don't know. So here, so you stay with your initial answer or you change your answer? Are you sure? So what you are seeing here is an experiment by which you get the feeling of what a state superposition is, okay? So if you are looking, for example, if I'm looking this image here, or if I'm looking this image there, I have the feeling that the image represents a situation that is not so clearly defined. I mean, I can say that the right box is looked from the bottom, but I can also say that the right box is looked from the top. It looks like that while I'm looking, I have the feeling that here the box is a superposition of one box that is looked from the top and one box that is looked from the bottom. So whether it's from the top or from the bottom, it depends on my specific choice in that specific moment. And this is actually what happens with the concept of state superposition. So what it happens is that the quantum entities typically are in a superposition of two states, top and bottom. And I only know the specific state when I'm doing a measurement, meaning I'm going there with my finger and I look whether this is from the bottom or from the top, okay? So this concept of state superposition is also represented by what is called the Schrödinger cat paradox, okay? Now I'm telling you the Schrödinger cat paradox. So here you have a cat that is inside a box. In the box, you have an atom, a radiative atom. Then you have a Geiger counter. Then you have a bottle with some E. What is E? With some prussic acid that is very poisonous. And therefore, it happens that when the radiative atom decay, so the Geiger count counts. The Geiger count counts, activate this hammer that breaks the bottle. The prussic acid exit from the bottom. The cat breathes the acid, and then it dies. Okay? Everything is inside the box. An observer from the exterior, with the box closed, cannot say whether the cat is alive or is dead. Because the probability that the cat is alive is 1 minus the probability that this atom has decayed. The probability that the cat is dead is equal to the probability that this atom is decayed. However, we don't know whether the atom, because we only know the probability. So there is 50% of probability that the atom decay, or 50% probability that the atom has not decayed. And therefore, we don't know whether the cat inside the box is alive or is dead. The external observer, without doing a measurement, should say that the cat is in a superposition of two states. meaning that the cat should be at the same time alive and dead. Note that the concept of superposition does not mean that the cat should be alive or dead. Okay? So the concept of superposition is associated with the fact that the cat is at the same time both alive and dead. So not is alive or dead. So it's not in a very well-defined state. What happens is that the state is only defined when we do a measurement, when we do interact with a box. In this case, so we are looking inside, and then we know whether the cat is alive or dead. Okay? So this is the paradox of the Schrödinger cat, and typically this means that the cat, in this case, is in a superposition state. So this 1 over square root of 2 is simply to get the normalization factor, but the cat is in a superposition of 2 states, one state where the cat is alive and one state where the cat is dead. And so this is the way to write the condition of the cat within the box. This concept of state superposition is translated into the concept of quantum bit. So in a classical bit, what we do have is that a bit can be in a state 1, a binary representation of the bits. So the bit can be in a state 1, and the bit can be in a state 0. Any other situation is an error. Okay? So this is the concept of the bit. In a quantum bit, what we have is that we are now describing a quantum system as a 2-level system, and the classical example is an electron, is the spin of an electron. But for example, if we are dealing with a photon, we can consider the polarization state of the photon. So either the vertical polarization or the horizontal polarization of the photon. And then the quantum bit is the state that represents the superposition between these 2 levels, between these 2 initial states. And so therefore, what you have is that a qubit can be represented as the superposition of a bit in the state 1 plus a bit in state 0, with a different C0 and C1 with a different probability. Okay? And so in this case, it means that when we are manipulating a qubit, what we are doing is that we are manipulating at the same time all the superposition state between state 1 and state 0. In digital classical computation, we only compute a bit, whether it is in state 1 or in state 0. So we are doing a computation on a single bit. In quantum computing, what we are doing is that we are computing on the qubit, meaning that at the same time we are doing the computation on all the different bits that can stay between bit 1 and bit 0, meaning 1, 099, 09995, 09995, 0999995, and so on and so forth. So at the same time, when we are manipulating the bit, so we have an enormous amount of information that can be processed. We say that we are doing a parallel processing of all the states given by the superposition of 2 initial states. At the end of the manipulation, what we do, we open the box and we look whether the cat is dead or alive. So that means that at the end of the calculation, so we make that the wave function, so the qubit state will collapse either in 1 or in 0. Okay? At the end of the propagation of our single photons, we know where the photon, the polarization state of the photon. Okay? So this is the concept of quantum qubit. And based on that, so people have developed a quantum computing. And so there was a big excitement about the quantum computing. So this is the announcement of a Canadian companies that is selling quantum computers. It's called D-Wave. And so this is the quantum computer of D-Wave. So if you want to do quantum computation, you can do quantum computation on this computer because they provide that in the cloud. Or this is the quantum computer that has developed Google. So you can go there and you can, so by the way, this is Indian. You can go there and you can do use the quantum computer of Google or IBM. So this afternoon when you will do a simulation and computation by using quantum computers, probably you are going to use the IBM quantum computers. So there are many different technological approaches which have been used in order to implement quantum computers. And so you have a platform that is the Ion Trap platform. So IonQ is a company that is selling quantum computer based on this platform. Then there is the superconducting platform. So you have to go down to cryogenic temperature in order to make the material transit into a superconducting state. But there are companies that are selling, so Google, IBM, and also European companies that are selling. So a quantum computer with, if I remember exactly, 10 qubits can be both, and the cost is about 10 million euro, just to give you an idea. So it's not like the cost of your laptop, 10 million euro for 10 qubits. So then there are companies in Canada, another one in New South Wales, in Australia, that are using spins. And then there are companies that are making quantum computer by using photons. So those two companies, they are PsiQuantum. So PsiQuantum is a company, is a Californian company founded by two British researchers that has a value of more than 1 billion euro. And they are claiming to be able to make a quantum computer with 1 million qubit in 5 years from now. So then there is another company. This is a Canadian company that is Xanadu, that is selling quantum computers. Nowadays they are able to sell, to make a quantum computer with 50 qubits. And this is also a company that is using photonics and is making the photonic circuit by using the silicon nitride platform. So this PsiQuantum is using silicon, and Xanadu is using silicon nitride. And then there are other companies that are selling quantum computer. QX is a company, is a European company that is selling a quantum computer. And even in Italy, we have companies that are selling quantum computers. So we are, personally, we are working with a company that is called Rotonium, that is indeed trying to sell a quantum computer. So where are we? Okay, so here we are trying to manage to develop quantum computers that are able to handle errors. And so this is a real problem, because errors in the computation means that at the end your result is useless. And there are many claims that in few years we will have a general purpose quantum computers. But actually, so the situation where we are is similar to this one. So this is the kind of quantum computer that we would like to have. And nowadays we have a quantum computer that is like, so that means that in order to have that the quantum computer overpass digital computers, so we need to be able to have a quantum computer able to handle a few thousand of qubits. And nowadays, so the record, I think, is 500 qubits. So we are still on the dawn of quantum computation. So this is an example of a quantum computer, actually a quantum simulator, that we have developed by using the technologies of the Bruno Kessler Foundation. I already said that in Trento we have the university and then the Bruno Kessler Foundation nearby, where they are making silicon photonic circuitry. And so the Bruno Kessler Foundation was handled this project. So this is a European project which is supported by the European Commission. And in this project, so we have developed quantum computers that is integrating every single characteristic needed for doing a quantum computation on a single circuitry, meaning that the photon sources, the scheme of manipulation of the single qubits, and then the circuit for detecting the single qubits. And so this is quite important because this platform has the advantages of being CMOS compatible, and more importantly, of being able to work at room temperature. So I said that one property is a single particle, the other property is state superposition, and then the last, but which is the most critical properties, is the entanglement. Any question up to now, or is it clear? Okay, let's go to entanglement. So Schrödinger, the father of quantum mechanics, was saying that entanglement, for me, is not one properties of quantum mechanics, but the trait, meaning that the real truth of quantum mechanics. Okay, so entanglement is really what is making quantum mechanics different from classical mechanics. And a couple of years ago, so those who were able to demonstrate entanglement by using photons have been awarded by the Nobel Prize in Physics. Okay? So this you should remember. So this is a French scientist, Alain Aspect. This is a German and Austrian scientist, Anton Zillinger, and this is an American scientist, John Clauser. Okay? And so they were able to demonstrate, John Clauser and Alain Aspect, the entanglement properties of photons, while Anton Zillinger was able to demonstrate the practical application in experiment like teleportation or quantum communication of the entanglement. And therefore, so they were given the Nobel Prize. So what is the entanglement? Entanglement was a concept that is quite difficult to understand because, for example, Albert Einstein was saying that quantum entanglement is not a real property. It's only a way that we are using because we are to describe what is happening in nature, because we are not good in developing a complete theory of what is happening in nature. The problem with Albert Einstein was the fact that he was not accepting the concept of non-locality. Let us try to understand the idea of the quantum entanglement. So let us perform this kind of experiment. So we have a source of photons, and inside this source of photons we have two photons. Okay? Then, what Albert Einstein was thinking was the fact that the two photons within the source had already very well characterized their properties. For example, let us consider that the photons within the source can be red or blue. Or if we consider the polarization state of the matter, can have a vertical or horizontal polarization. So Einstein was thinking that within the box, the two photons, the properties of the two photons was already established. Then it happens that the two photons, the blue or the red, are sent to two observers, which are typically called Alice and Bob. And now Alice is looking at the photon and is observing that the photon is blue. Therefore, she is thinking that if I have got the blue photon, so then Bob should have got the red photon. At the same time, Bob is looking at the photon, is observing that the photon is is red, and therefore he immediately thinks that Alice has got the photon red. Okay? So this is what Einstein was thinking that nature behaves, how nature behaves. So the state of the photon is predetermined, is already intrinsic in the source. Quantum mechanics, on the other hand, is saying that each single photon is in a superposition of two states, the red and the blue. And therefore, in the source, the photons are both red and blue. Then the two photons are emitted by the source, and they maintain the fact that they are in a superposition of two states, red and blue. But what happens is the fact that the two photons are correlated, meaning that here we have a photon that is both red and blue, and here we have a photon that is both red and blue, but the state of the two photons are correlated. Now, the photon reached Alice. And now you have the collapse of the wave function that happens during the measurements, meaning that you start with a situation where you have a superposition of two states, then you do the measurements, and then you end up with a very well specified state. The wave function that was a superposition of two states collapsed on a single state. That means that here the photons was in a superposition of two states, red and blue, and while Alice is doing the measurements, the wave function collapses, and then as a result of the measurements, Alice is measuring that the photon is red. This is the result of the superposition and of the measurements. But quantum entanglement tells us something more. Since the two states are entangled, are correlated, what happens is the fact that when Alice is doing the measurements and the wave function collapses to a state, very well-defined state, this collapse of the wave function happens also on the photons that Bob is measuring. And what happens is the fact that immediately when Alice is doing the measurements, the wave function of the photon in Bob's hands collapses to a state that is the counterpart of the state measured by Alice. So that means that in one measurement, you have that the two photons are emitted, you get that Alice is measuring red, and Bob is measuring blue. In another measurement, you have that Alice is measuring red, and Bob is measuring blue. In another measurement, Alice is measuring blue, and Bob is measuring red. And so the outcome of the measurements cannot be known a priori, because this is the result of the superposition of the two states But what we know immediately is the fact that when Alice measured a state, Bob immediately measured the other state. And this was something that Einstein could not accept, because Einstein was saying it's not possible that the correlation between the two states is preserved even though the two states are not on the same physical position. So the non-local properties of quantum mechanics was something that Einstein was not understanding. So here we are dealing with the non-local properties of the quantum mechanics. So entanglement is preserved even though the two particles are physically separated. Let us go back to the Schrödinger cat. The Schrödinger cat is nothing else than a state where we have an entanglement between the cat and the decay atom. So this entanglement is even preserved if I do cut the box in half without doing any measurements, without looking inside the box, and then I will send the cat to Delhi and the atom to Nagpur. So very much separated, a couple of thousand of kilometers, of 1,000 kilometers, I don't know. So they are very much separated, but they are in entangled state, meaning that the cat is in a superposition of dead and alive, and the atom in a superposition of decayed, being decayed or not. As soon as I open one of the two boxes, I have the collapse of the wave function. What does it mean? It means that if I'm opening the box in Nagpur, I see that the atom has decayed, and immediately I know that the cat is dead. The state of the cat is dead. On the other side, if I'm opening the box in Delhi, I look inside the box, I see that the cat is alive, and I know that the atom is not decayed. And so this is an intrinsic properties of quantum mechanics that can be used in order to make devices, in order to make a concept like quantum teleportation, in order to enable a concept like entanglement. So this property is called the entanglement and is associated with the concept of non-locality and express the concept of the quantum correlation. So if we go back with to the Schrödinger cat, so this is the way that we are writing the wave function that describe what is happening inside the box. So we have an entangled state between the cat and the atom, where we have a superposition of a two-particle state. So here we have two particles, meaning that we have the atom and the cat. And in one state, we have that the cat is alive and the atom is not decayed, and this state is superposed to another state where the cat is dead and the atom is decayed. And so this is a superposition of the two states. And so in this superposition, we have that the cat is on the same time dead and alive, and only when we do observe the situation, we have the collapse of the wave function, and we have that the cat is dead or alive. Okay? So the take-home message is, do not open the box if you do not want to kill the cat. Because if the box is closed, the cat is still alive and dead at the same time. So the same you have with the photons. So, and the way we use in order to make those entangled state is to manipulate the single photon state. Okay? For example, in this sequence, so we have our qubit, which is a single photon, and we are considering the polarization state of the photon. Then, what we do is that by using an external mean, in this case, we are using a laser, for example, so we force the two photons to make an entangled state between one photon in a polarization state and another photon in another polarization state. And so what we do now is the fact that now we are writing the wave function that describe the fact that we have a superposition we have a superposition between the two photons. So one photon is photon 0. Are you familiar with this way to write, to describe the state? So here what I mean when I do that is that I'm describing the state, okay? Then what I put here is the characteristic, the degree of freedom of the state that I'm describing. For example, if I have a photon that is in the polarization state, that is a vertical polarization state, so then what I'm saying, I'm describing the degree of freedom of my photon, and since the photon is in the vertical polarization state, I put here V, okay? Then I may say that I'm trying to describe in two photons, one photon here and the second photon there. And therefore I have the way I'm saying is that this photon is in this state, this wave function is describing this photon, and I call this photon photon 0. It's just to label the photon. And this wave function here is describing this other photon. And I say this is the photon 1, okay? Then what I'm doing is that now I do force, by using the laser, this photon state into I'm forcing this photon into a well-defined polarization state. For example, the vertical. And therefore, what I'm saying now, if I do want to describe a photon that has a vertical polarization, I will add here the cat. So this is called the cat. The cat of the vertical degree of the polarization degree of freedom. And therefore, now I have the product between V and 0. A shortcut notation is to say that now I have this state where I have photon 0 in the vertical polarization state. And here I have photon 1 in the vertical polarization state. So what does it mean? It means that now I have two photons. I have two photons. One photon that has an horizontal polarization, and the second photon that has a vertical polarization. But those two photons, you see the plus, those two photon states are correlated, are entangled. But those two photon states are entangled, okay? And here it is represented, this entanglement, by the chain. So they are strongly related. Clearly, I don't know what is the polarization state of my photon. If I'm sending my photon away, and here I have a photodetector, I don't know whether in this photodetector is the photon 1 that is coming or is the photon 0 that is coming. And therefore I have that the result of this, the state of my photon along this path can be either a photon 0 that is vertical and a photon 1 that is photon 0 that is horizontal and a photon 1 that is vertical. I don't know which one is here because they are both sent away. And I can also separate those physically, locally separate. One I can send in Beijing, and the other one I will send in Vienna. And then I will do the measurements and I will get the Nobel Prize. Anton Zillinger has got the Nobel Prize because of an experiment where he was able to send entangled photon state with along a very long distance. And so the two qubits here, the two photons, are entangled. everything changes if I'm doing a measurement. So if I'm doing a measurement, what happens that as a result of the measurements, I know whether the photon was this one or the photon was that one. And so what happens is that while I'm doing the measurements, I will measure a given photon state. For example, the photon 1 in the vertical polarization. But then now, since the two photons were entangled, now I know immediately that the state of the other photon is the horizontal one. Okay? And so this is the properties of the entanglement. So this correlation is preserved even if the two photons are separated. And when I'm doing a measurement, so then I have the collapse of the photon in a very well-defined polarization state. And immediately the information of this polarization state is transferred to the other photon. Now we have another properties that can be exploited in order to entangle photon states. And so this properties is the contextuality of the quantum mechanics. What does contextuality mean? Contextuality means that, remember the box into which we had the two balls. So we have the box with the two balls. Contextuality. So we have the two balls inside the box. What I was saying is that the box, so the color of the box is not predetermined. Sorry. What I was saying is that the color of the ball is not predetermined. Classical mechanics is saying that the color of the ball are predetermined, so this is red or blue. Classical mechanics say that the color of the balls are predetermined. So we know in advance, so the color of the ball is an intrinsic properties of the ball, and within the box, the ball could be or red or blue. Quantum mechanics say that this is not true. What happens is the fact that within the box, the ball is in a superposition of state where the color of the ball is at the same time red and blue. And it's only during the measurements that I'm determining the color of the ball. So contextuality means that during the measurements, the color of the ball is determined. So that means that the properties of the ball, the color of the ball, depends on the context, on the measurements that I'm doing. It's not predetermined a priori, but it depends on the measurement I'm doing, on the context. If I'm doing the measurements, the ball turns out to be red. If you are doing the measurements, the ball turns out to be blue. It's like if you are looking to a man, and this man is in a superposition state of the color of his skin. If I'm looking at this man, I see that this man is black. If you are looking at this man, you see that this man is white, or vice versa. Don't know. So it's the measurements, it's the person that is doing the measurements that determine the state, the color of the skin of the man. And so this means that we do have that the ball is at the same time in a superposition state between the blue and the red. So this is a very important properties of the quantum mechanics that differs substantially from what is happening in classical mechanics. Einstein was not happy with this. Einstein was saying that quantum mechanics is an imperfect theory because it's not able to describe how nature is working. On the other side, Schrödinger and the other father of quantum mechanics were saying that, no, it's not true. So quantum mechanics is a good theory of nature. The problem is that quantum mechanics has properties that classical mechanics does not have. Contextuality, and as a result of the contextuality, the properties of non-locality. Non-locality, what does it mean? It means that the entanglement is preserved even the two particles are separated. Contextuality means the properties of the particle is determined by the way I'm performing the measurements. And sometimes the result is a result, and sometimes the result is a different result. It depends on the measurements. With the measurements, I do force the collapse of the wave function. And so what we did in the past, and I will talk about that tomorrow, is that we are also able to produce quantum correlation, so entanglement, not having two particles, not having a particle that is red or a particle that is blue, two different particles, but within the single particles. And, and what we are doing is that we are producing a quantum correlation between two different properties of the same particle. Let us give a simple example. So what we are doing, so if you consider your man, you have that the man can be black and white, or you can have that the man is tall or short. And therefore, so what you can do an entanglement, so black and white, or tall and short. And so therefore, what you can do, you can write an entanglement between those two characteristics of the man. So this means that the man can be black and tall, or the man can be white and short. And so what you do is that you entangle, you correlate those two properties. If you do a measurement, so you have that the wave function of the man collapse on a very well-defined state, that means that now the man is black and tall. But this is produced by the person, because of the contest, by the person that is looking at the man. Another man, another observer, can get a different results. Okay? And so what you have is that you have entanglement on a single man between those two characteristics of this man. And what we have, we will talk tomorrow is how it is possible by using those properties to make and to enable a new device. So here is the ingredient, the basic ingredient of quantum system that are exploited in quantum technologies. So the single particle, the entanglement, and the state superposition. Now the problem is, how can we integrate all those properties within a single photon chip? And so what we have to describe is, how do we generate these single photon or these entangled photon sources? How do we manipulate the superposition state? How do we process those single photons? And then, finally, how we do perform the detection. So, the problem is to have a generation stage, meaning that we need to have lasers, we need to have single photon sources, and this is going to be the topics of the next lecture. And then we need to have a manipulated stage of the photon state, the quantum photon state. And in the manipulation stage, what you have a standard photonic component that we already know, Mach-Zehnder, beam splitter, couplers, and things like that. And then we have finally the detection stage. And the detection stage is made by detectors, by filters, and the requirement on the detector and filters are very, very, very stringent, meaning that we need to have detectors that are able to detect the single photon. We need to have filters that are able to filter out up to the single photon level. So a few last considerations before the break, just to give you an idea where we are. Okay, from the point of view of the hype, from the point of view of the expectation, so at the beginning of, let's say, in the first 20 years of 2000, so people was looking at the quantum supremacy. Quantum supremacy means that the quantum computer will be able to do things at a very much larger speed than a single computer, a single digital computer. So we will demonstrate that with a quantum computer we can do anything better than a digital computer. But when we say better, it means that we will make things with an exponential time advantages with respect to the quantum, with respect to the digital computer. Then, while developing the quantum computers, people started to say, not actually a quantum supremacy, but we will demonstrate an advantage by using quantum computer, meaning that we can do the same things with a digital computer and with a quantum computer, but what we will do with a quantum computer will be things that have an advantage in terms of power consumption, in terms of speed. Then, in these last couple of years, people are thinking about the use of quantum computer in terms of having a utility in addition to what we already have. And so nowadays, the concept that is dominating in the field is the fact that we will have, at the end, a computer which has inside a computer different utility block, like we have a CPU, like we have a GPU, so central processing unit, graphical processing unit, a TPU, tensor processing unit. We will have a quantum processing unit. And therefore, those calculations where a quantum calculation will improve, the performance will be performed by the QPU, while those calculations, for example, artificial intelligence, will be done in a GPU, or those calculations, for example, sequential operation, will be done in the CPU. So the computer will be able to drive the specific part of the calculation to the unit that is able to perform this calculation in a better way. So, which could be the GPU, the QPU, the CPU. And therefore, so the quantum computer will not replace the digital computer as it was expected at the beginning of the second quantum revolution, but will complement the standard digital computer by adding more functionality in the processing. This is also reflected in the so-called, I don't know whether you are familiar, Gartner hype cycle. So this is a way that Gartner, that is a foundation, an American foundation, is representing how a technology is evolving. I don't know whether you are able to read, but this is the expectation as a function of the time about a technology. So you start with the discovery, so the trigger of innovation, so the development, and then the expectations start to rise. Then you have a peak in the inflated expectation. So all the people are saying that there is a lot of hype about this expectation. All the people want to invest, so there is a big expectation. So this new technology will change the way we are living, and so on and so forth. So then after this peak, so you have a drop in the expectation that is called the disillusionment period, and then you have the slow growth of the actual deployment of the technology, which means that now you have what is called the plateau of productivity. Okay? And so this is the way that the technology, from the point of view of the expectation, typically evolve. And so Gartner, what they are doing is they are placing all the different technologies along these curves. In 2018, so quantum computing was in this position. So in 2018, all the people were very excited about quantum computing. All the people were very excited about quantum communication. All the people wanted to invest in quantum computing. And what you see here is the fact that you have that quantum computing was even larger than artificial intelligence. A big investment push in quantum computing. So then, last year, Gartner produced the next hype cycle. And what happens is the fact that in 2023, so last year, few years after ChatGPT was public in 2022, so the year after, and so what you have is that on the top on the peak of the expectation of the hype, there was generative AI. So that means that all the people is investing in generative AI, because there is a huge expectation of. And what is funny here is the fact that quantum computing disappeared. Okay? So even not in this range here. So quantum computing is gone. And the reason why is that here people were saying in 5 years we will produce a general quantum computer that is able to do everything better than the other, exponentially better than the other. But then, during the development of the technology, people realized that quantum computer is still at the level of research in the lab. Okay? And therefore, so it went out. What is the reason of that? What we need to do in order to push again quantum computing in the field of view, in the market. So let us see what happened with artificial intelligence, because we can get some insight in this evolution of technology. So you know that artificial intelligence nowadays is booming. I mean, if you have to prepare a document, so you write the document by key points, and then you give the document to an artificial intelligence model that is processing. Okay? So everyone is using artificial intelligence. But where is coming the hardware of artificial intelligence? So the hardware of artificial intelligence is coming by the development of graphical processing unit that are processors that have been developed for graphical representation. Essentially was the gaming industry that was pushing the development of this technology. No one at that time was thinking about artificial intelligence. So the application was a gaming application or image processing application. So no one was thinking to artificial intelligence. But then, when the models of artificial intelligence start to appear, so 2015, AlexNet was demonstrated that is based on, oh, now I missed the word, okay, that is based on deep learning, okay? So deep learning appeared in 2015, and then from the deep learning, due to the fact that technology, the GPU technologies was there, so everything boomed. And so therefore now, so people is thinking to do something similar in quantum technology. So people are thinking, so if the development of the quantum computer is so difficult, And moreover, if the development of quantum computer cannot be sustained by a market of quantum computing, so what should we do? What kind of technology based on quantum technology we need to afford in order to be able to develop all the infrastructure then will be taken over by the quantum computer later on. And so let us look at the quantum technology supply chain. So here you have the market value of the different component in a quantum technology supply chain. So here you have the end user, and here you have those who are developing the quantum hardware. And you see that those that are developing the quantum hardware are making the most of the market. And which one is this quantum hardware that people are developing? So the quantum hardware that people are developing is quantum sensing. Okay? So the actual push of the development of quantum technology is not the computing, but is the sensing, is the measurement. So if you want really to have an impact in quantum technologies nowadays, is not to go to quantum computing, but is go to quantum sensing. Because in quantum sensing, there is the actual market. And quantum sensing have many different applications. Here, I'm showing you the technological readiness level, so the level of development of a technology for different application of quantum technologies. So the larger is the technology readiness levels, means that the largest is the development of the technology, so the more ready to the market the technology is. And what you are seeing here is that there are a few technologies that are already on the market, magnetometers, the quantum cryptography, the post-quantum cryptographies. And there are other technologies that are still far from the market. The quantum computing has a technology readiness level which is very low. And therefore, so that means that the readiness of the technology in quantum computing is much smaller than the one in quantum cryptography, is much smaller than the one in quantum sensing. Yes, I finished. Yes. And this is the reason why, if one looks at the forecast of the market, what typically you see is the fact that the sensing market is the one that now is growing a lot, while the computing market is predicted to grow once the quantum computer will be there. And so this graph here shows you the status nowadays of the quantum technologies. So we have a very good quantum sensor, quantum measurement system that are indeed produced in the market, and still people are trying to push the quantum computing, even though the quantum computing market nowadays is not yet ready. Okay? So this is, with this I finished the introduction on quantum photonics. Do you have any question? Yes? I cannot hear.
How is it possible? You were explaining about Schrodinger cat thing, and if I separate the two boxes to a larger distance, obviously the probability of cat dying will be changed, right? And how is it possible? I did not get that feeling.
Okay, so the question is quite good question. So the question is, so I do have two things that are entangled, okay? And the question is, how can I preserve the entanglement over long distances? So the question is a very important question that is about the argument I did about the error in quantum computation. That is the very similar question. So for how long the properties, the quantum properties of the qubit are preserved if the qubit is interacting with the environment. And this is indeed one of the most urgent problem that has to be solved in order to make a quantum computer viable. So the maintenance of the qubit state, the coherence of the qubit state over a long time. Because what happens is that you are manipulating the qubit, so after the first manipulation, the qubit state is still a single particle state, very well defined. The second manipulation is still a very good quantum state, is conserved. But then, if you increase the number of manipulations, you lose the quantum properties of the state. And therefore, you lose the quantum properties of your qubit. And this is exactly what you are saying. So how can I preserve the entanglement over a very long distance if my qubits are interacting with the environment? And indeed, this is what happens. So the quantum correlation properties are lost if the photons or if the quantum state interacts with the environment. And so the only way to do that is to generate many entangled states with the hope that after a certain distance, a few of those are preserved. But then what you have to do is that you have to develop a technique that enables you to say whether the photons that you have sent over a long distance is still in a good quantum state. Okay? And therefore, what are there, we will talk about that as well, are techniques that enables you to measure whether the entanglement is preserved. This technique is called the measurements of the Bell violation, and we will discuss about the measurements of the Bell violation. But your point is is a very good point, and this is also the reason why a quantum computer is so expensive. It's so expensive because people are trying to isolate at the maximum the quantum computer from the environment in order to reduce the coherence, is called, of the quantum state. Thank you for the question. Other question? Yes?
When we are talking about entangled states, and one of the particles is sent to Alice and one of the particles is sent to Bob, we always say that they are measuring the states at the same time. What will happen if one of the party, like Alice, measures its state first, and what happens to the second state if it is not?
Okay, so this is also a very good question. So it's about a synchronization between the measurements in two different places. Okay, so if I want to exploit the entanglement, so the question was about the fact that if I want to exploit the entanglement, I need that the measurements of Alice and the measurements of Bob within a certain time interval are performed at the same time. So this is the problem of the synchronization of the measurements. Because if Bob is measuring 1 hour later, okay, it may measure another photon that is not the photon that was entangled with the one that Alice is measuring. And so if I want to exploit the entanglement properties in a communication link, I need to be sure that the measurements are really very well synchronized. And so there is a problem of synchronization. From the point of view of the entanglement, if Alice is measuring, the state of the particle that reached Bob, even though Bob is not measuring that particle, is already determined by the collapse of the wave function of Alice. So if Alice measures red, the photon in the lab of Bob, even though Bob is not measuring, is getting blue. No choice, no chance. The problem is whether Bob is able to measure this photon or not. But the fact that the entanglement caused the collapse of the wave function of the photon of Bob, the measurements of Alice caused the collapse of the wave function of the photon in the Bob labs. So this is not questioned. So this is happening. The problem is whether Bob is able to measure. Okay? I don't know whether I have answered to your question. Okay? Good. Other question?
Does there exist any relation between special theory of relativity and quantum
The
Does there exist any relation, like as we were talking about time? So in special theory of relativity, we have time delay, time advance.
Okay, so this is another story. So this is also one of the reasons why Einstein was not in agreement with the concept of entanglement. So Einstein was saying it's not possible that an information travel faster than the speed of light, okay? Because this is the basis of the concept of relativity. But then there is the question about what is information. So is entanglement transferring any information or not? Okay, so this is the actual point of the questioning. So entanglement is not against is not against relativity. Okay, so they are coherently, because people say that the paradox is solved because if Bob wants to announce the result of his measurements to Alice, he can only do that by a classical channel. Classical channel means he has to call and say that. And therefore, this information, so the information that the result of the measurement of Bob is a blue particle, is traveling to Alice through a classical channel. And therefore, the relativity is not violated. You see? But then in quantum theory, the concept of time is not like in classical theory. So the concept of time in quantum is not well defined. And the entanglement is also preserved in time. So there is the theory of procrastination by which the result of a measurement in the future affect the state of a particle in the past. Because the time in quantum mechanics is not very well defined. If you are interested in quantum procrastination, I can give you some reference on that. I will show you tomorrow, I guess, or today, some experimental measurements that we cannot understand with standard classical intuition. One is this on quantum procrastination. So the measurements done tomorrow will affect the result, the state of a particle of yesterday. But this is actually measurements that people have done. So they are result of the measurements. Okay. Other question? So if not, we can take a break.
So we'll have like half an hour break. There's tea and biscuits outside, and again we'll start again in half an hour for the next session. Okay.